Well, welcome to my last lecture on defects in conformal field theory. I'll be leaving right after the lecture today. I have to run back to England. So if you have questions, try to ask them during the lecture, because I won't be here this afternoon. I guess there's nothing this afternoon anyway. But if you have something that's occurs to you later, feel free to send me an email, especially if you have any comments about the notes, which I just sent a revised version of the notes last night. Probably they'll appear on the website by and by, which I think has essentially everything I'll say or have said over the last week. Although it's also very rough. I mean, part of it was scribbled in at close to midnight last night. Anyway, if you're not tired of listening to me after a full week of these lectures, I'll just mention that I have a YouTube channel where there is a defect-free version of these lectures. They'll go by much more quickly because they were heavily edited for clarity and precision, but they're also free of boundaries and defects and so forth. So for that, you'll have to look at the recordings from this workshop. I believe all the lectures are going to be online, so there's a library of stuff that's available to you. Anyway, today I'd like to talk about trace anomalies. This long-promised lecture. It's a bit closer to the stuff I've actually been working on over the last few years, so I hope I can answer more of the questions, although in some sense I won't be able to, because it's also a little bit closer to the frontier of the field, and so there are a lot of open questions I don't know the answer to. So this is about cases where, even though we have classical Weyl symmetry for our quantum field theory, the stress tensor nevertheless is not zero. And so if it's not zero, the question is, what is it? And so this is a lecture about the different possibilities. I'll just remind you of something you're already familiar with, I think. If you've had a good quantum field theory course, you've probably studied QED for maybe a massive electron. And I believe if you go and you compute the trace of the stress tensor in that theory, it's a theory for which the photon is not going to introduce any problems classically. But nevertheless, if you go and you compute a one-loop diagram, you look at the photon propagator in the presence of this matter, and the vertex, I guess it all comes from the vertex. Sorry, not the vertex. It all comes from the electron propagator, the self-energy for the electron. There's a beta function for the coupling, and that shows up in the trace of the stress tensor. And if it was massive, another thing you could see would be the m psi bar psi bit, the mass of the electron. Because masses make things not traceless. They've introduced scales. This would be dimension 3/2, plus 3/2 is 3, plus 1 is 4. So it has the right dimension to be sitting on the right-hand side, and indeed you'll see it shows up classically. So you could cross that out. You could make your electron massless, but still charged, and that's what happens. And you still have the beta function. So this is a story today not about those kinds of cases. It's about conformal theories, right? It's about cases where we have a CFT in flat space, and so we've arranged for all the contributions from the sort of ordinary fields you're interested in, the electromagnetic field, the spinor fields, the scalar fields, all those things won't contribute, even at a quantum level. And so in flat space, it's zero. But we still have a question. It's what happens in curved space. And this is a very interesting story because there can be a contribution to the trace anomaly from the curvature of your space-time. And very famously in 2D, So this is the one time in this series of lectures where I'm going to spend, excuse me, I'm going to spend a lot of time talking about the 2D case because it's so remarkable. You find a contribution that comes from the Ricci scalar curvature. So that R is the Ricci scalar. And there's a coefficient there, C, which winds up being super, super important in the study of two-dimensional conformal field theories. And the experts, I know there's some of you in the audience of on 2D conformal field theory probably already know most of the items in my list here, but let me go ahead and list them anyway for those of you in the audience who haven't spent that much time thinking about 2D conformal field theories. So here's my non-exhaustive list of why that C is so important. One is the statement that CUV is greater than CIR. So if I have a notion now, say, of some general two-dimensional quantum field theory, I know the fixed points. I have a UV fixed point and an IR fixed point where the beta functions vanish. Those are CFTs. And so this central charge, this C central charge, is providing an ordering on the space of my 2D QFTs under our renormalization group flow. So if you give me two arbitrary conformal field theories and one has a central charge that is less than another, I can automatically tell you which one cannot possibly be the UV fixed. There's already an ordering. So that's quite an interesting statement. It was proved by Zamolodchikov many, many years ago in the early 80s. Here's another reason we care about it. C fixes the stress tensor two-point function. I mean, we saw in our lectures that stress tensor two-point function is already fixed up to a number. Before I didn't really say what that number is. Now I'm telling you what that number. That number is the same number that shows up in the trace anomaly for 2D conformal field theories. And I'll show you how that comes about later today. This one I won't prove. There's a nice paper, you can read it. It's not so bad. This one we'll do today. Another thing that's, I think, quite interesting that we'll also do today, I hope, is that it fixes, so this is flat space. This is the flat space case we studied. It fixes T mu nu in curved space. If you tell me C, I can tell you what the stress tensor is in curved space, and you also have to tell me a little bit more data. You have to tell me how to Weyl rescale a flat space to get the curved space you're interested in. Because in 2D, there's this remarkable fact that any metric is conformally equivalent to the flat metric. So I can rescale by some function, local function of the coordinates, multiply it by a Kronecker delta function, and that gives me the curved metric I'm interested in. So if you tell me this, I can tell you that, as long as I know what the central charge is too. And we'll see how that comes about later too. I always thought that was really neat, so I thought I'd share it with you. It has a name. This is the Schwarzian derivative. And one of the reasons I thought I'd show it to you is usually in these courses, they just present the Schwarzian derivative. They say, this is what it is. You can check that it's right. I often did that in my own lectures. Some other things, I can't remember now. These finite conformal transformations. I just said, this is the special conformal transformation. You can see that it's the right form by looking at the infinitesimal limit. But in this case, I'll derive this for you, which I think is kind of nice. And then, right, there's a special case of this. Here's a curved space. Well, it doesn't really have curvature. It's still flat, but it's related to a flat plane by one of these conformal transformations. And so by using the Schwarzian derivative for a cylinder, I can learn the equation of state for a two-dimensional CFT. It goes as pi ct squared over 6, where T is the temperature. So you tell me C, I can tell you how the energy density depends on temperature. And the idea here is that you're thinking about time, Euclidean time. So there's some beta, which is the length of this, or circumference of this cylinder, which is related to the inverse temperature. And there's, of course, another way of looking at this, which is as a Casimir energy. If I think of this as a space-like direction, and time is just the direction along the cylinder, then I get a Casimir energy, which is negative because of the way Wick rotations work. So this C is also telling me the Casimir energy of my 2D CFT on a cylinder. So the picture to have in mind, I really have a cylinder, and there's a length, which is beta, or 1 over t, and then there's another direction. And then so depending on how I interpret it, I can get two different very interesting results. And last thing I might note, for those of you who care about such things, there's this concept of entanglement entropy. I haven't talked at all about this, but there's close connections to a lot of this defect work with entanglement entropy. And here, the entanglement entropy of an interval is also fixed by C, the length of the interval and some UV cutoff, because entanglement entropy winds up being not particularly well defined. It depends on UV cutoff, but there's some coefficients here which are universal, which are these trace anomalies. That's a nice long list of why people think C is super interesting. It's all well known, and I think probably for some of you, I'm telling you what you already know very well. But I bring it up for a reason, which is to motivate the study of these anomalies in greater generality. I mean, it naturally suggests a couple of questions, which are, can we find similar phenomena in D greater than 2? And the answer in many cases is a qualified yes. And okay, I just sort of presented you with a fait accompli, but in order to really extend this work, we've got to try and figure out what was going on in the 2D case. What are the rules that gave us this result? T mu mu equals C over 24 pi. Can we really drill down and understand that case and thereby figure out a little bit how to extend it and go beyond it? Okay. Questions so far? So for how many people is this list, laundry list, kind of a well-known set of items? Can you just raise your hand? I'd like to see. I think that's less than half. Okay, good. So I'm glad I went through it. I'm never quite sure who my audience is here. But I think it's a very remarkable list. If you haven't seen it before, it's like, wow, you have a lot of power in 2D CFT. You know a lot of stuff. Good. I'm getting ahead of myself. So I'm going to fall back on my friend dimensional analysis to try and understand what's going on. First point of call for me, essentially all the time. So let's think carefully along these lines. So if I'm studying this stress tensor, and I've already sort of by assumption said it's not going to depend on any of these other fields, Maxwell field, scalar field, so on and so forth. So then what's left for it to depend on is the curvature. And probably I'd like it to be something nice, analytic behavior. So let's assume it's some kind of polynomial in the Riemann tensor. That seems to be what happened in the first case. So this guy has dimension d, right? And this guy has dimension d over 2. And so if I'm forced to construct the trace in this way, this must be a polynomial of degree d over 2. And it's a polynomial, it's not just a polynomial, it should be some kind of scalar quantity, right? This is a scalar. It's a scalar on the left, and so I'd better contract all my indices on the right too. I better not have any hanging Lorentz indices or space-time indices over there. So already from this kind of simplistic analysis, I can conclude a couple of interesting things. One of which is that there's nothing in odd dimension. I simply have nothing I can write, because I would need to write something that has odd mass dimension, and I only can construct things that have even mass dimension if all I can work with is the Riemann tensor. And the other thing I find out immediately is that in 2D, R is essentially the only possible thing I could write down. Got to contract all the indices. It has to be already dimension 2, so it has to be linear in the Riemann tensor. And so, what else can you do? So it's sort of an example of Murphy's law. So this is the only possible thing that could show up on the right-hand side in the trace. Anything that could possibly happen will happen, and it does. That's a little bit too trivial. So let's look at a more complicated case. Let's look at 4 dimensions and think about that. Let me try to crowdsource this. So what are some things I could write down in 4D based on this set of rules? Yeah, Ben? What's that? R? So in 4D, this stress tensor has what mass dimension? It's mass dimension 4. So on the right-hand side, I need it to be a polynomial of degree 2, right? So not just R, but I could certainly have R squared. What else could I have? Gauss-Bonnet. Absolutely. I guess this is sometimes also called the Euler density. Anything else? Weil squared. So you've already seen the answer, I'm gathering by the answers. What else? I'm missing a big one. There's one left. I guess I'm being a little unfair because I didn't quite include it in my set of rules on the top board. Yeah, box R. So these are already pretty elaborate combinations to consider, and indeed they're going to show up for reasons that I'll make clear in a minute. But let's back up and write them in their constituent form. As I have, clearly I can contract the Ricci tensor and I can contract Riemann. And finally, box R. And I think that's all I have. So there's 4. There's 4 possible things that can contribute. And it turns out that there's really only a 2-parameter family that's physical. So there's some other conditions that I haven't yet mentioned that we can bring to bear to kind of clean up the situation. and make what appears on the right-hand side a little bit more rational, and focus on those two terms that the members in the audience brought up, Weil squared and the Gauss-Bonnet or Euler density term. Right, so what did I want to write? Let's write the answer. So here's mu. It's a conventional normalization. In fact, there is no conventional normalization. Every single paper on this seems to choose a different one. A for D, let's call this Euler density, and C for D, I can call it Weil squared. Why are only those two showing up? And let's put a little bit more meat on what I mean by the Euler density. So the Euler density, for those who don't know, mu1, mu2, mu3, mu4. I have a four-dimensional epsilon tensor in 4 dimensions, so I'll write down 2 of them. And then I'll go ahead and I'll contract the Riemann tensor in the following non-obvious way. And I have a couple of claims. One is that this can be rewritten as a particular linear combination of I don't know how I should write this. How about C1? That's probably a bad. I already have C. Oh, we could do C1. All right, C1 Riemann squared plus C2 Ricci squared plus C3 R squared. There's some particular choice, C1, C2, and C3, for which that is equal to this, right? So, and also you notice those two indices are antisymmetric, so I'm contracting them with antisymmetric indices down here on epsilon, and so this whole thing works. So that's the first remark. And the second remark is that this integrates, it's a nice topological curvature invariant. It integrates to the Euler characteristic on your manifold. So there's some alternating sum of Betti numbers which agrees with that integral over the whole surface. So for some reason that's showing up, and we'll get some intuition why in a minute. And the other one is this W squared is the Weil squared, Weil curvature squared. And I'll be non-specific about how the indices are contracted, but again, there's some other particular linear combination of these 3 guys, which is Weil squared. So I'm picking out 2 very special combinations of those monomials in the curvature. And are these coefficients interesting? Well, we saw in the 2D case, C was quite interesting, so there's some hope they're interesting here as well. And I'll just point out, again, a non-exhaustive list of why you might care about those coefficients, A4D and C4D. One is that C4D fixes the stress tensor 2-point function, and another is that a combination of A4D, C4D, and one more, which I won't write down, fixes a 3-point function. So 3-point functions are fixed up to numbers. For scalars, it was just one number, but for tensor structures, there'll be more than one number typically. So just like we saw in the 2D case, these numbers are fixing correlation functions of the stress tensor. And there is also there's a close connection. They also fix, I'll just note this, universal pieces in entanglement entropy computations. So that's another point of similarity. I think that's all I wanted to mention so far. How did this, where am I? I mean, I should also mention, of course, there's a there's a similar C theorem that A4D UV is greater than A4D IR. Right. And that explains this minus sign. I've chosen this minus sign here so that I can write the result that way. So again, these trace anomaly coefficients are providing an ordering on the space of quantum field theories under RG flow. Okay, so those are some reasons to care about this. And now I wanted to explain why just these two particular linear combinations. So there's two reasons. The first goes by the name Wess-Zumino consistency. And the second reason is related to the possibility of having local counterterms and there being some ambiguity in the precise way these QFTs in curve space are defined. So let's think about this. So imagine, let's go back to our path integral point of view. So imagine we have some kind of effective action W, and I'm in Euclidean here, so there's no i's, which is related to my path integral, which I'll write schematically as some integral over fields, e to the minus s phi, where again, I'm thinking about this in some Euclidean setting. And I want to know what happens to my quantum action here under rescaling the metric by some function. And, right, so I'll get some formal result here that delta sigma w is equal to minus the integral d dx. That minus sign, I think, because of Euclidean, square root of the determinant, t mu mu delta sigma. Where now this is not necessarily zero because I'm doing more than just a classical analysis. This is in the context of the path integral. Now, these variations, these Weyl variations, they form an abelian group. Right? It shouldn't matter which order I perform these Weyl rescalings by local functions. The Weyl variations should commute. So if I take delta sigma 1, delta sigma 2 of this effective action, that should be the same as delta sigma 2, delta sigma 1 of W. Okay? And that's our first condition. That's the condition of Wess-Zumino consistency. And I'll just note that there's, if you had a non-abelian group, there would just be a more complicated rule here, but you could still talk about Wess-Zumino consistency. Whatever structure the group has, it should be reflected in how these variations commute, how these a repeated variation with respect to the group element commutes. In our case, it's just abelian, so it's nice and simple. And so we should be able to check very straightforwardly these terms I wrote down that I just erased, whether they satisfy this or not. So let's look at one of these terms. Let's look at r squared. R squared delta sigma 1. Okay, so the result of doing our first variation, first Weyl variation. And now what I want to do is I want to do a second one, delta sigma 2 of r squared delta sigma 1. And I claim that the result of this, and I'm being a little sloppy, I'm not writing the whole integral and the measure and so forth, but I claim that the result of this is r delta sigma 1 box delta sigma 2. So I leave that to you to check that, when you rescale Ricci scalar in 4 dimensions, there's a linear term which goes as just a Laplacian. But this is a problem, because the way that sigma 1 and sigma 2 are showing up is not symmetric. And you could say, well, let's just integrate by parts. Maybe I can integrate by parts and symmetrically distribute the way these derivatives act, but there's an r in the way. So even with integration by parts, it's not Wess-Amino consistent, at least not on its own. So it's not something we could consider adding to the right-hand side of the trace anomaly. It wouldn't follow from this action principle. Now the terms we did add, on the other hand, I'll point out, do satisfy this condition. Let's just think about them. So if I take delta sigma root g of this Weil squared term, well, Weil squared has very nice properties under Weil rescaling, because you've trace subtracted all this stuff out of Riemann to get Weil. And as a result, it's just sort of covariant with Weil transformations, and that square root of g in the integral is going to soak up the rest, and so this just vanishes. So this is kind of trivially Wess-Amino consistent just on its own. I can do the second variation, it just vanishes. It clearly doesn't matter which order I do it in. The second one will always kill it. The second one is a little bit more interesting, the Euler density guy. So I take delta sigma 2 of root g of my Euler density. And remember, I already have a delta sigma 1 there. And now this, I claim, varies to a total derivative. That requires some work to see, but it's not terrible. Times delta sigma 1. So there'll be a delta sigma 2 in here somehow, being acted on by lots of stuff. But the point is that now I can sort of distribute the derivative in a symmetric way, because there's nothing else in the way, there's no additional r. And so after integration by parts, it is WZ consistent. So it's something I can add, but it's a little bit less trivial the way it happens, because there's this total derivative that shows up and I've got to integrate by parts. Now there's an interesting consequence or difference, or this difference is often highly stressed in the literature. People often talk about type B and type A anomalies. And there's a physical consequence here too. Let's just point that out. I mean, I lied a little bit when I said there's nothing else in the way. Let's write it down a little bit more carefully. So in principle, we have A4D sitting there. Some stuff that I'm not being careful about, delta sigma 2, delta sigma 1. And so if I integrate by parts, I could hit A4D, right? And up to now, we've just been assuming it's constant. But what if it's not constant? Could it depend on something? What's a case where it could depend on something, possibly? Yes, that's a very good point. So indeed, if I have a boundary, I have to improve the Euler density by a boundary term. There's a well-known example of that in 2D where the Euler density is just Ricci scalar, and the boundary term is the Gibbons-Hawking term. But that's actually not what I was after, but thank you for the comment. So in 4D CFTs, there's the possibility of having marginal operators. and correspondingly marginal couplings. These are, marginal couplings have no dimension, right? And so I could possibly worry that A4D is a function of those marginal couplings. Let's call those couplings lambda. And just by locality, maybe I have some situation where, I tune the coupling in one part of the universe to be something and some other part of the universe to be something else. And so maybe these could actually depend on space-time as well. Just seems like I ought to be able to have that freedom. Excuse me. But this rule here is basically saying that if I want to be able to add this term to the trace, A4D had better be independent of marginal couplings. It really needs to be a constant. The only way this is going to show up in the trace anomaly is if that A is a number that characterizes the theory uniquely on the conformal manifold, on this space of conformal couplings, if it exists. Great. Yeah. That's right. I don't have, if I'm working in curved space, I don't have this full conformal group. I could, my metric could break translation invariance. So I'm thinking about this in a curved space context. Right? And then at the end of the day, I'll push myself down to some flat space limit and consider a conformal field theory in that flat space. So I'm deducing consequences about the theory from the possibility of being able to write it in curved space. I think this is a very subtle point you bring up, and it's one that often troubles me, but at the same time, it's a very powerful idea that you ought to be able to define a quantum field theory on whatever manifold you like, and that introduces this host of additional constraints. And I think there is another point of view which just says, I'm happy working in flat space. Forget this general consistency point of view. But then you have less power, so I don't know. But this is a question you can ask about a lot of stuff people are doing, not just in this context. I think it's an important question. Okay. Where am I? Right, enough about Wess-Amino consistency. So that was 3, and now I'm on to 4. Counterterms. Let's do counterterms. It's sort of the same story, at least from a technical point of view, but the conceptual bit is going to change now. So, in RG, we need counterterms. Counterterms for masses, counterterms for kinetic terms, counterterms for everything you write down in your action. And in curved space, that's no exception. You need local counterterms there as well. And one possible counterterm you could write down would be r squared. How about r squared? In your RG procedure, it could well be that you need to adjust your effective action by some r squared term with some carefully chosen coefficient, I don't know, k. And how you add that counterterm is probably even going to depend on your renormalization procedure, whether you use dimensional regularization or what have you. That number will depend on exactly the details of your UV completion. So it's not it's in some sense not physical. Or it can only become physical if you also specify what the UV of your theory is. You give me some extra information. Now, we just showed on the left-hand board there that delta sigma r squared looks like r box delta sigma. And so after integration by parts, this is the same as box r delta sigma. So this means I can remove box R from the trace with a counterterm. That's one way of saying it. There's some other ways of saying it too. That the coefficient of box R is not physical, because it depends on your regularization scheme, it depends on your UV completion, or you could say it's there, but in a way that is sensitive to UV physics. And this is kind of a bummer, actually. I mean, I wrote this paper a while back with my graduate student at the time, Kuo-wei Wang. He's now a postdoc. And we were trying to figure out like the generalization of this Casimir statement. I told you that in 2D CFT, you can figure out the Casimir energy on a cylinder, basically just using the trace anomaly. And we'll see how that works a little bit later. But here there's a problem. So if you try to run the same trick here, there's this box R term that's kind of in the way, and it's going to show up. Like you could try to compute, the analog here is going to be the Casimir energy on a sphere cross time, because that's your cylinder, like an S3 cross time. You can indeed compute the energy contribution to that Casimir from the physical anomalies, from the Euler density term and Weil squared. Well, Weil squared won't contribute because spheres are conformally flat, but from the Euler density term, you can compute that contribution to the Casimir. But box R pollutes it in this way that's sensitive to your UV completion. So that's a part of the story that now kind of diverges when you go to higher dimensions. You can't reliably compute the Casimir energy in general. Although there are exceptions to that too. I think like in supersymmetric theories, you can further constrain the coefficient of this box R term, as I think Davide Cassani has shown in some of his work. He's sitting there in the audience, yeah. All right. So that's the idea. So that eliminates R squared because it wasn't Wess-Zumino consistent. It eliminates box R because you can remove it by counterterms, and it just leaves our two combinations, which are these special combinations, the Euler density and Weil squared, and that's why those two show up in 4D and why they're picked out and they're special. And people often just forget this. They don't even write it down, but you should remember it's kind of there. Good. So let's go on to boundaries and defects, unless there are questions. So the beauty of these defects and boundaries is that you're able to get, at least we believe you're able to get, defect or boundary localized contributions to the trace. So sigma here is my defect. So there's some delta function, I don't know quite how to write that, which localizes you on the defect. And then there's going to be some polynomial. So this is still dimension D. This has dimension Q, which is D minus P. That's what's localizing you on the defect. And so what's left is a polynomial of dimension D minus Q, which is some, again, we can use Riemann. And now we can also use some notion of extrinsic curvature. Maybe I should write it as the second fundamental form. So there's something new. So I jumped the gun there. So this is still here. This is still Riemann. That's still there. But there's something new you get when you have a defect, which is a notion of extrinsic curvature. How that defect is embedded in the ambient space. And while this has weight 2, this has only weight 1. It's only basically a single derivative, like a single derivative acting like on a normal vector, or two derivatives acting on the embedding function, but that again is just dimension 1. So there's an interesting difference here, point of departure from what we had before, which is that odd dimensional defects can have a trace anomaly. Or at least that same argument I used before, where I just have weight 2 objects. Now I have a weight 1 object, and so I'm able to, if I have a 3-dimensional boundary, I can construct something which has weight 3. All right. So I have an hour left. Got to really start thinking about how to use this time wisely. I have a sort of 3-part plan. It's kind of ambitious at this point. I wanted to flesh out the bullet points for the C in 2D. Then I wanted to show you how you can treat the 2D manifold as a surface defect and what changes in the trace. And finally, I wanted to give you a very brief tour of defects in more than 2 dimensions. That was my plan for the rest of my time with you. Are there questions before I begin? So this 2D stuff is really beautiful. I think it's part of why so many people spend so much time studying 2D CFT. You'll get a little bit of a taste of that now as I go through some of these derivations. So I want to begin with a question. So we saw that the trace has this form in 2D of C over 24 pi, integral d2x, root g r delta sigma. And the first question I'd like to ask is, what is W? In some sense, this is a differential equation for W, right? It's saying the derivative of W with respect to the Weyl parameter is blah. So I can't tell you the whole answer, but what I can tell you is how it changes as I perform a finite Weyl transformation. I can give you the difference between the effective action on a general curved metric. Remember I said in 2D, that is a general curved metric. I can always cast it in that form. That's a very special fact about 2D. It's very important for string theory, in fact, that that's true, minus what you get in flat space. It's about all I can do. I mean, there's going to be some integration constant when I solve this differential equation that I can't really fix. And one issue that we'll see is that this winds up not being local in the original variables. It's kind of a non-local object. And so a sort of standard technique for dealing with these kinds of non-localities is to introduce additional fields, massless fields, which will allow me to write down a local expression, but which if I integrate them out, make it non-local. So there's a trick is to introduce, people call it a dilaton, which is going to have a nice transformation property under Weyl. Tau goes to tau plus sigma. And this will let me integrate up or solve this differential equation in basically by guesswork. You can repeat this procedure in higher dimensions, and people have done it, although there maybe guesswork doesn't work so well. But anyway, for what we're going to do, guesswork is just fine. So I'm going to guess. So if that's my rule, then let's guess that, guess one is that I'll just multiply what I had by tau. Seems like it might almost work. Because then when I shift tau by the Weil transformation, delta sigma, I pull down exactly what's on the top line. Now there's a problem with this, of course. We know that the Ricci scalar also transforms under Weil. So this is our guess. The problem is that if I look at how R transforms, and I guess I've already written down this twice, but let me write it down one more time in a slightly different way. It's worth checking if you've never done it. Minus 2 sigma R of G mu nu minus 2 box sigma. And this is a 2D variation rule. There's also a rule in general D which has an additional quadratic piece in sigma, but we don't need it. This is the 2D rule. So, right, there's a problem, right? If I vary R, I'm also going to pick up a tau box sigma piece, which isn't up there on the first line. But in the disease lies the cure. You've seen other things which will vary to produce something like tau box sigma, or box of variation. You saw it in the first or second lecture. It's just a free field. Free field varies to produce box free field. That's the free field equations of motion that are basically sitting here. So we can fix things up. We can fix our guess in a trivial way. Minus c over 24 pi integral d2x root g r g mu nu tau minus d tau squared. So by adding that kinetic term for tau, I mean, the equation of motion for that from that piece is just the box tau, right? I can cancel out what's spoiling me here from varying R. Should we do that in slightly more detail? I claim that's the answer. People see it? Yeah, question? Nope. G is the curve metric. G is e to the 2 sigma delta mu nu. This is just telling you what the transformation rule is for so I could write it, yeah, I could write it in terms of, really I just want the infinitesimal variation. So I don't really care about this full thing. Maybe we should just do that. And then in that case I could cross out that. Well, I can't really cross it out, but anyway, that piece will cancel against the root G piece. And it's this piece that I'm worrying about. Yeah, I mean, the details will slow you down, and I'm being a little bit quick here. The details certainly slowed me down last night when I was trying to make sure all my signs were right. So we just check that we get the right answer. So I have d2x root g. I do my variation. So I get delta sigma from the first term. That's the one I want to keep. Then I get minus 2 box delta sigma tau from varying R. And now I have minus 2 d tau d delta sigma. And, sorry, that's d tau. And now I integrate by parts, and these two terms cancel. So why am I saying that the original guy was non-local? Let's try to get rid of tau. Let's try to integrate out tau. So by that I mean let's find the equation of motion for tau. I claim that's r equals minus 2 box tau, just by varying tau, integrating by parts again. And then I can use that to replace tau in my action, at least formally. And so on shell, I have w is minus c over 12 pi integral d2x root g r 1 over box r. This action, I think, is often called the Polyakov action, although you should, I think, distinguish it from the action you saw in the strings lectures. And because of this 1 over box, this is the non-locality I was talking about, the fact that you have some kind of notion of an inverse derivative. You can run this procedure again in 4D and 6D for those anomalies in higher dimensions. People have done that. I'll just point out that in those cases, you'll typically get things that start with d tau to the 4th, because it has to be weight 4. Or in 6D, there's a 6D anomaly. You'll get something even more complicated with 6 derivatives acting on tau. But let's focus on the 2D case. Keep. So the first thing I want to do is I want to compute the stress tensor 2-point function using this action. Okay? Convince you that you can do that here. So let's write this guy in a slightly nicer way, a more precise way, as a double integral. d2x prime root g prime d2x root g r of x 1 over 4 pi log x minus x prime squared times r of x prime. Now, how did I know that that was the same as this? I'm using this fact from electricity and magnetism when you solved for potentials in the 2D plane, that box on 1 over 4 pi log of x prime squared is a delta function. And hopefully I've got all my factors of 4 and minus 1 correct. Okay, just the usual fact that the potential for a point charge in 2 dimensions is a logarithm, or a potential equivalently for a line is a logarithm in 3D. So morally, this is this object here is like the identity over box. And so now what I want to do is I want to consider a small fluctuation. I'll take g mu nu is flat space plus some small fluctuation. And you can check. I did this on Mathematica last night because I didn't believe the source I was copying from. This is an argument that comes straight out of chapter 3 in Polchinski, if you haven't seen it. Chapter 3 is a chapter well worth reading. So I claim that at linear order on the fluctuations, in complex coordinates, I'm in 2 dimensions, so it's nice to work in complex coordinates. There's a linear order contribution to the Ricci scalar, which has this form. Second order derivatives of, it needs to be weight 2, right? So that needs to be a 2 of these metric fluctuations. So I'll go ahead and I'll plug that in here. And we'll see what we get. And we'll see we quickly are able to get the stress tensor two-point function. So let's go. So W at this linear order is minus c over 48 pi squared integral d2z integral d2z prime, because now I'm able to drop the square root g's because I'm working close to flat space. dz bar squared log z minus z prime squared, and then these metric fluctuations. Okay, so now I'll integrate by parts. So I can act with this partial on the log, and I can act with that partial on the log. And I'll pull down out a factor of 3 factorial, or 6, and a minus sign. And I should get c over 8 pi squared integral d2z, d2z prime, hzz, hzz with the primed coordinates, and then z bar over z bar prime to the fourth. Now my definition of the stress tensor is a variation of the metric with respect to metric fluctuations, right? So I can vary now W with respect to this guy, W with respect to that guy, pull down two stress tensors, and so directly from this formula I see that T with upper index ZZ, another T with upper index ZZ, but at the prime coordinates, this is C over 4 pi squared. There's some factors of 2 in the definition of the stress tensor, and there's another factor of 2 from this being quadratic. So the 8 becomes a 4, and then 1 over Z bar minus Z bar prime to the fourth. So there we have it, folks. So the stress tensor two-point function is fixed by the central charge. And there's another component, which is the Z bar component, just the complex conjugate of what you've written here. And all the other components have to vanish because, well, the stress tensor is traceless, remember? And in my complex coordinates, if I'm going to take a trace, the only non-zero components of my flat metric, let's see, delta Z, Z bar by abusive notation, this is the only component, these off-diagonal components are the only ones that are non-zero in complex coordinates. And so this has to vanish. So in particular, these components have to vanish. And so those don't show up in the two-point function here. It's just these diagonal components, and it's holomorphic conjugate. So we've completely fixed this stress tensor two-point function by the central charge here, which I think is quite nice. So if you have your favorite theory, like a free scalar in 2 dimensions, you can go and you compute the stress tensor by usual means, by, you write it down, use Wick's theorem, use the propagator for the free scalar field, and you'll find, I hope, if you do it right, that C equals 1, which is why, going back, when I wrote down the original trace of the stress tensor, I put a 24 pi there. So that now when you go and you compute C for an actual example, maybe our nicest example, simplest anyway, you find C equals 1. Right. Questions about this? There's some subtle details here, like cross terms, like why did the cross term vanish? But, yeah. Yeah. That's right. What I'm doing here, I should emphasize, I'm very close to flat space. I am looking very close to flat space. And so the question you want to ask probably is best asked for my next example, when I'm going to try to argue I can get at the one-point function for the stress tensor in a general curve background. But I think the claim is that it works. That the one-point function that I'm going to get in a general curve background, I can get that way. It's not somehow this. It doesn't matter. Where am I? Oh, 8. Here we are. So if people are happy with this otherwise, I'm going to move on to the curve space case of the one-point function, which I think is another really super beautiful example in 2D CFT. So if you've never seen it, I think this is kind of a treat. So T mu nu in curve space. And this is my own idiosyncratic way of getting there. I think most textbooks take a completely different route to the same result, but here we go. So I claim that if I want the stress tensor in this curve background, I can get it from varying my effective action over there. At least I can get the difference between that and the flat space case by varying the action with respect to the metric. And I'd like to argue, in fact, that I should just be able to set that to 0. So in fact, I'm going to get the whole answer this way. And what I'm assuming here is that in the plane, in the vacuum state, by symmetry, the stress tensor should just vanish. Seems like a reasonable assumption of the vacuum in 2D conformal field theory, that I don't want it to have some non-zero energy density. But I don't know, if you're not happy with that, I guess at best here I'm computing some difference. So I vary with respect to the metric, use my definition for the stress tensor, and there's some obvious pieces here which come from the kinetic term for the scalar field. You already did this. This was an exercise. And then there's some non-obvious pieces which come from varying the Ricci scalar. But you did this also because I asked you to do that super important exercise about verifying that the scalar was Weil symmetric for some particular coupling with the Ricci scalar. So that's the same thing that you need to do here. So here's the rest of these pieces. So here's another contribution from the kinetic term for the dilaton, and another contribution from from varying the Ricci scalar. This is my improvement term for the stress tensor in a slightly strange way, written in a slightly strange way with tau instead of phi squared. And I'll make one additional comment that you might have expected to find some piece from varying the Ricci scalar. So you might have expected to find some contributions from the Einstein-like equation contributions from the Ricci scalar term, something that looked like this. Because remember, when you vary Einstein-Hilbert, you get something like this from varying the inverse metric that contracts the indices of Ricci's and varying the determinant that multiplies that Ricci scalar. So these pieces come from varying the Ricci scalar, the Ricci tensor, but these other pieces often show up in any kind of derivation of equations of motion in general relativity. But I'll just point out that in 2D, Einstein's equations are trivial. And so this tensor is just 0 for us. We don't have to worry about it at all. It doesn't show up in this metric variation. The only thing we have to worry about are these 4 terms here. Yeah.
Maybe I should have asked this before, but are you considering tau a background field, or are you considering tau was
this is supposed to be an effective action, so it's something that shows up after I've done the path integral. It's supposed to control the correlation functions. So I guess the answer to your question is this is an external field. It's something I fix along with the metric.
So the correlator on the left-hand side is computed with respect to all the other fields but tau.
Yeah. So this isn't quite in the form I want yet. So what I want to do next is I want to get rid of tau. So I'll use the equation of motion for tau and replace it with the Ricci scalar. And I'll also note that I'd like to work in a frame where the metric is just Weil equivalent to the flat metric, in which case I can also write the Ricci scalar in the same way. And so thinking a little bit carefully about how I want to set the integration constants of those two equations, I'd like to argue I can just swap sigma for tau on shell. So wherever I see tau in that, I can replace it in terms of this Weil rescaling factor sigma. So let's do that. And I'm going to do a little bit of last-minute trickery here as well, whose details I won't show you. Something else that was slowing me down last night checking this, various minus signs. So I'd like to write this just now with respect to some kind of background flat metric instead of in the curve metric we had on the top line. So I want to replace the covariant derivatives with just ordinary flat space derivatives, and that's going to have some connection term discrepancies which I can adjust for, it turns out, just by flipping the sign here. So instead of having plus d tau, I'll get minus and making that swap. And there's a similar sign shift in the next line, although we're actually not going to care about this part. Delta sigma squared minus box sigma, where this will now be the flat space box. And again, there's a sign flip here for the quadratic term, if I remember right. So I'd like to write it just sort of with respect to some flat background, make my life easier. These are things I think that can all be done fairly efficiently by hand, although at this point in my life I tend to like to speed things up with Mathematica, so I was checking this last night with Mathematica. Anyway, we're almost there. We're almost there. So if I'm say I'm in a curved background that I'm going to use the coordinates w to describe, and I want to get there by some holomorphic change of variables, from some flat space metric. I know because this is a conformal theory, I should be able to write that as e to the 2 sigma g z z bar. So from this I can identify sigma as 1/2 log z dwz plus 1/2 log dw z bar. And we can do some more here. We can do dw sigma is z double prime to z prime, and dw squared sigma is z triple prime over 2 z prime, z prime squared over 2 z prime squared. So I'm doing this to cast this object in a more familiar form for those of you who study conformal field theory, sort of more traditional form. And now let's look at the WW component of the stress tensor in this non-flat background. I claim or this coordinate change background, I claim I can write this in the following way: dw sigma squared plus dw squared sigma. Because in complex coordinates, this piece just disappears, so I'm just looking at the diagonal piece of the stress tensor here, so I only have to worry about the first two terms. I plug in my rules for how to do this coordinate change. And I find that this is C over 24 pi to these peculiar combinations of holomorphic derivatives of my variable change to dwz squared, which is often written in the following way. This is the Schwartzian derivative for the stress tensor. So I always kind of like this derivation. I mean, so often in CFT courses, we're just presented this kind of with a fait accompli. We say this is the Schwartzian derivative, and we can show that that's how the stress tensor fails to be a conformal primary in the language of 2D CFT, and relate it to this central term in the Virasoro algebra. But here it's sort of coming out at you from an orthogonal perspective, from the perspective of this trace anomaly, sort of a direct computation starting from curve space and landing you at the end with the exact form of it. Are there questions about this? Should we do something with it? Let's do something with it. Get at one more bullet point on my list of why C is so important in 2D.
Using the same technique, you can also compute dw bar.
Mm-hmm. Yeah.
So you can reconstruct this whole trace anomaly.
The full trace anomaly. You can, full stress tensor, yeah. You can get WW bar, it's just the complex conjugate of what I've written, yeah. Yeah. Yeah, that's right. That's something I should emphasize, that again, in 2D CFT, there's just basically two components of the stress tensor. These two, the off-diagonal ones, those correspond to the trace in our rectilinear coordinate system. Those vanish. And this guy, we've done this guy, we can get that guy just by taking a complex conjugate. Yeah.
Yeah, but if the trace is not vanishing,
Yeah.
we are discussing a trace anomaly.
Yeah. So, right. So, I mean, I guess secretly, if I'm just doing a change of coordinates, I'm not really going to a curved space anymore, I guess. So I guess the Ricci scalar should vanish, right? If sigma, so general sigma, this wouldn't be true. But for sigma that's related to this change of coordinates, the Ricci scalar, of course, will continue to vanish. So I'm just doing a change of variables here to get at the Schwartzian derivative. So in this language, I'm still in flat space, actually. If you want the curved space result, you've got to go back to this language where I've written it in terms of sigma. And sigma then might not be of that particular form, a product of a holomorphic and an anti-holomorphic function, or the sum of a holomorphic and an anti-holomorphic function. Do you see? Sorry, yeah, I should have made that point clearer. So this is the answer for the one-point function in general curve space. And then in CFT, we often just care about changes of variables, this sort of or diffeomorphisms, or going from one coordinate frame to the other. And if I do this, I'm not going to change the curvature. So if I start in flat space, I'm going to end with a flat space, and there'll be no contribution to the trace of the stress tensor. But there is nevertheless a non-zero stress tensor that comes from this coordinate change. They're conformally flat, but they're not flat. They'll depend on box sigma. And here at box sigma, since these are purely holomorphic or anti-holomorphic, box sigma will vanish. And box in complex coordinates is dw bar. Yeah. Yeah, thanks for that question. So let's do a cylinder to plane mapping. So W will be x1 plus I x2, and x2 will be periodic. So I have in mind some kind of cylinder. So that's my x1 direction, and that's my x2 direction, which has a length beta. And I want to do a coordinate change. Z is e to the 2 pi w over beta, and I claim if you start on the cylinder, you'll end on the plane, if you have this kind of a definition of your coordinate domain for w. Okay? So, if I want tww on the cylinder, this is c over 24 pi, my Schwartzian derivative. I go and I plug in to my formula over there. I get c over 24 pi. I see there's basically an overall factor of 2 pi over beta, which I can factor out. 2 pi over beta squared, there's like a z to the fourth in the numerator and a z squared in the denominator. So overall, when I take these derivatives, there's a fourth order derivative in the numerator, a second order derivative in the denominator. So when I take these derivatives, I'll get an overall factor of 2 pi over beta. And then there are just some numbers I have to compute here, 2 minus 3 over 2, from taking those combinations. So what is this? This is minus c over 48 pi, 2 pi over beta squared. And we can do two things with this. We should go back to our rectilinear coordinate system to make physical sense of what's going on. So I know if I go back to the 2, 2 and 1, 1 coordinates, that t2, 2 is minus t1, 1, has to be, otherwise it's not traceless, and that winds up being a following combination of my holomorphic and anti-holomorphic parts of the stress tensor. So I add up what I had at the top, and I get minus c over 24 pi, 2 pi over beta squared. And now there's two possible interpretations here. Let's think about x1 as being Euclidean time. That means my time stress tensor is really minus t11 by putting in those two factors of I to go from Euclidean to Lorentzian. And I wind up finding this is minus pi c over 6 beta squared, and that's my negative Casimir energy. And then the other thing I can do, I guess I can, let's do it over here, x2 to be Euclidean time. So now this is a periodic Euclidean time, and we know that means temperature. In field theory, T is 1 over beta. Now T, the time component of the stress tensor is minus T22 is pi c t squared over 6, the equation of state for my 2D CFT. I sort of beautiful consequence of, starting with a trace anomaly. You get all these kinds of different consequences. The two-point function of the stress tensor in flat space is fixed. You get these non-trivial shifts of the stress tensor, even when you go from one flat space to another by these holomorphic coordinate transformations. And you get the stress tensor one-point function in curved space in general, too, if you don't want to restrict to these particular kinds of sigmas whose box vanishes. All right. Questions about that? So the last 20 minutes or so, I'll give you a sort of brief survey of what's going on when I promote this to trace anomalies with defects. So that's the end of the calculations I'll show you. At this point, I'm just going to say words. 2D manifold. So instead of thinking this 2D manifold as the manifold on which my conformal field theory lives, let's think about it as a surface defect in some larger spacetime. And I claim then that there's additional contributions to the trace anomaly. I have the one I've been talking about at length up to this point, this Euler density term. So this is some intrinsic Ricci scalar, just like we had before, although now we're thinking about this 2D manifold in some larger space. But we have other objects to play with now. We have this fundamental form, second fundamental form, or extrinsic curvature. And we can build something quadratic in that has the right properties. And in fact, there's a third thing we can write down which is a bit surprising. It turns out this is not the only way we can contract the indices anymore if we're in this defect setting. Since the tangential and the normal indices play a different role, we're free to look at other ways of contracting the indices of the Riemann tensor. And one way you can do it is you can take VII and you can contract just over the tangential indices. So there are these two new terms that appear if I treat now this 2D manifold as part of some larger structure. And this can be shown using exactly the same techniques we were talking about in the 2D and 4D case without defects and or boundaries. It can be shown using this notion of Wess-Zumino consistency and independence of counterterms. Okay. So what's known about these new terms? So I found this kind of exciting when I first saw this. So that, well, so much is known about the 2D case. Maybe there's something interesting to be said about these new terms that show up that people haven't really looked at that carefully, at least not yet. Let me tell you a few things that are known about them. There's an A theorem or a C theorem again, that if I think about UV and IR fixed points, this A associated with the surface defect, the UV value of it is greater than the IR value. But there's an important caveat here. This is a statement about a defect RG flow. So in these lectures, we made an important distinction between operators that live in the bulk and then operators that live on the defect. So if we want to make the statement, this is about an RG flow where you add just some relevant operators on the defect, that live on the defect. And with respect to that RG flow, the UV value has to be bigger than the IR value. If you put stuff in the ambient space, things are quite a bit more complicated. And in fact, another curious difference is that A sigma, while it's insensitive to marginal or defect marginal couplings, so that's like the C and the A4D, A4D, that we discussed before, that there's a West-Amino consistency constraint on that the C and A in the bulk couldn't depend on marginal couplings. Here that's restricted to the defect case. And in fact, there's something rather interesting that happens about the bulk marginal operators. So imagine you have some pair lambda and O, where that's a marginal operator. What you find is that you can take a derivative of this A sigma with respect to lambda, and you can pull out the 1-point function. Let's just write a constant of proportionality. The 1-point function normalization of the operator O. So the O here would be equal to CO over some distance to the D power. So since it's marginal, it has dimension D. It's a 1-point function in this defect or boundary CFT, and so it's allowed to have a 1-point function. That normalization determines how these guys change with marginal parameters. And so then it makes it much less natural to think about that as some way of ordering theories, defect theories, by bulk RG flows, because even on the conformal manifold, this guy will shift around. So depending on your starting point for your RG flow, it's hard to make a statement like this, because already this is sort of shifting around as you shift the marginal operators. Right. Say a few more things. How about B1? So this B1 trace pi squared. So this is this second fundamental form. I won't derive it. That's one of these important quantities for differential geometry. If I put a hat on it, it becomes traceless. And here there's some way of contracting the normal and tangential indices, which makes a scalar quantity, and that contributes. And because it's traceless, it winds up being basically trivially West-Amino consistent, because if I take the Weil variation of this object, so that's some boundary or defect metric. If I take a Weil variation of this, this just vanishes, just like the Weil squared term in the bulk. And so it's a natural candidate for something to add to the defect action. So I won't tell you too much about this. Often when I give this talk, I perform the following derivation that you can relate B1 to the displacement 2-point function. But I don't think I'll do that now, since I don't really have time. I mean, the intuition is the following, that you can think of this pi AB as being like a second derivative of the embedding location of your surface defect. And so since it's showing up in an effective action in this form squared, you can take two derivatives with respect to the embedding location, and it pulls down a second derivative of the displacement operator. And so by comparing, this anomaly action, which has this sort of scale contribution to the displacement two-point function, you can fix the normalization and make that relation. I've got 10 minutes left, and I've got a lot of other things I want to just sort of sketch out. So that's B1. And then B2, is interesting for a different reason. So again, this winds up being kind of trivially West amino consistent because the Weyl variation just vanishes again. It's the Weyl tensor that's showing up there, and the Weyl tensor has nice properties under these scale transformations. Now it turns out that B2 goes as H, where H, if you remember, was the constant I used to determine the one-point function of the stress tensor with a defect. So again, the intuition there is kind of the following, that you can think of the Weyl tensor as some kind of second derivative with respect to a metric. So if I vary my anomaly action with respect to the metric, I pull down a single stress tensor, and then by comparing the coefficient there with the coefficient of the full one-point function, I can fix H in terms of B2. Now, I said something a few lectures back, I don't know if you'll recall, but I said that only scalar operators get one-point functions in boundary theories, and that you need to consider a defect theory in order to get a one-point function for an object like this. So what's gone wrong then? What do you think happens in the case where I have a two-dimensional boundary and a three-dimensional bulk? How do you think this system gets around that constraint? How do you think the system knows that the stress tensor is going to vanish in that case? Any thoughts? You may have had to have some good GR course to know the answer to this. So the Weyl curvature tensor doesn't really exist in 3 dimensions. It's trivial. And that's how the system gets around it. So in the 3D bulk, 2D boundary case, that last term here is actually absent. And so there is no one-point function for the stress tensor in the presence of a boundary. Good. Yeah, kind of running out of time. That's too bad. I've got 2 more pages and only 5 more minutes. Well, we'll do what we can. We'll do what we can. Yeah, I can, but my cab is also coming, so I have to be a little careful. And my flight is not very far away, so I'll take a few more minutes. So these are early days in studying these coefficients, and you can ask lots of questions like, for supersymmetric theories, are there relations? Are there relations between these coefficients? And it turns out that for SUSY theories, there's a conjectured relation between B1 and B2. There's actually only one independent coefficient, is the conjecture for B1 and B2. And that's been proven in several cases. I mean, it's a little bit dependent on what kind of supersymmetry is there. Another thing you could ask about bounds. Now, there's a couple of obvious ones that, or not so obvious ones that follow from what I've written on the left here. One is that B1 had better be positive. That's reflection positivity. If B1 is determined by a displacement two-point function, two-point functions had better be positive by reflection positivity. And so That's bounded. There's something else called the ANEC, the average null energy condition, which is a statement about integrating the stress tensor along some null geodesics. So that if you want your system to satisfy the ANEC, then H should be 0, which should also imply that, say, B1 is greater than 0. Although the signs there are going to depend a little bit on your conventions on how you set up the trace of the stress tensor. Right. And then we can go on and talk about a higher dimensional case where, sort of less and less is known as we go up in dimensions. The 2D case is always a good place to start. I'll just sketch out a few things, and then I'll wrap up. So one case that I've worked on quite a bit is the 3D boundary 4D bulk case, in which case there's two contributions to the trace anomaly. One looks like extrinsic curvature times Weil, and another one looks like extrinsic curvature cubed. So in the boundary case, extrinsic curvature kind of replaces that second fundamental form. And so in this case, we know a couple of things. We know B1 is related to the displacement 2-point function, and it's also, as we saw in the lectures, related to the stress tensor displacement 2-point function. There's some kind of word identity there. And B2 is related to the displacement 3-point function. So if you know these guys, you know these guys. So that's nice. And now we're really getting to the kind of frontier of the field. So last week, I had a paper with a bunch of co-authors in Southampton who honestly, I have to say, did most of the work. I was freeloading a little bit on that paper, I confess, but so it goes. So 4D case. Just last week, acknowledge important contributions by my collaborators who were Andy O'Bannon, Jacopo Sisti, Brandon Robinson, and Adam Chalabi. So in this 4D defect case, there's more than 20 terms. And of this, there may be only 3 that we can say something about. I mean, you can kind of guess what they might be. There's something that looks like a derivative acting on extrinsic curvature contracted with Weil. So again, I do my counting. 1 + 1 + 2 is 4. Has to be 4. This is related to a displacement 2-point function. There's one that's a second derivative of Weil, so 1 + 1 + 2 is 4. This is going to be related to a stress tensor 1-point function. And then finally, there's an Euler density term, and there should be some corresponding A theorem for defect flows. But that's only 3 out of 20, and the rest is kind of open season. So there's a lot to do. So I can maybe use edge in a dual sense here. We're talking about edges, boundaries, defects, but I think also this is a important sort of edge or frontier in our field more generally of high energy particle physics. I've taken you on a very long journey. I think we started, physics of the 70s, the 80s, and ended up here at a paper from last week. But for those, now it's your turn. You have to take over now. I hope I've inspired some of you to look a little more carefully at these things, and I'll leave you with kind of a surfing analogy here, right? Like it's been this long journey. It brought you to this border between the land and the sea. Some very beautiful Point Break. I have in mind Southern California, where I did a postdoc many years ago. The conditions are kind of perfect, I think, for making progress or for finding that perfect wave. And it's not crowded yet. You've gotten there really early in the morning, or the weather really sucks, so people haven't quite showed up yet. And I brought you right to the perfect spot to catch that wave, right to the drop zone. And the next wave is yours to ride. So thanks.
So thank you very much. I guess on behalf of all organizers and all students, we would really like to thank you for this great set of lectures. And yeah, the lecture notes, the exercises, they're available on the website. And now I guess we should let Chris run to catch the cab and the plane. Thank you very much.